Hello everybody. So today we are going to discuss the second topic under non-muscle physiology, that is resting membrane potential or RMP. So if you look at the word resting membrane potential, so first of all, resting means when the cell is not getting any kind of external stimulation or inhibition, that is known as the resting stage of the cell. In most of the cases, in resting stage, cell remain in equilibrium condition, right? And second thing, potential. The potential means it is nothing but voltage, charges. So, if I want to understand the literal meaning of resting membrane potential, then suppose I have a cell like this, okay? So this cell is under resting condition, means in an equilibrium condition. In this equilibrium condition, if I measure the voltage difference or potential difference between inside the membrane with respect to outside the membrane, between inside with respect to outside the membrane, then that membrane voltage difference, that potential difference is known as resting membrane potential. So what I told, I repeat, okay? I told that if I measure the voltage difference between inside with respect to outside, means during measurement of resting membrane potential, always we take the outside at the reference point. So outside or the ECF side of the membrane, it will act as a reference side or reference electrode, okay? And the interior or inside of the cell, that will be taken as the active electrode or recording electrode. This is by convention, you cannot change it. So that's why we always say that inside with respect to outside, the voltage difference is known as the resting membrane potential difference. In most of the cells, okay, the RMP ranges from minus 10 millivolt to minus 100 millivolt. Different cells have different resting membrane voltage. We will be discussing that a little later, but for the timing, you remember that it is the potential difference between inside with respect to outside, and range is from minus 10 to minus 100 millivolt. Now if I want to measure the resting membrane voltage, so what I have to do, I have to put one electrode through this cell membrane, means I have to pierce through this cell membrane, and I have to introduce one electrode inside the cell membrane, and I have to put one electrode outside the cell membrane, and in between these two, if I connect to one voltmeter, that can record the potential difference between two leaflets of the membrane, inner leaflet and outer leaflet. Getting my point? So the electrode that I have to introduce through this membrane, that has to be very, very fine, that has to be very, very thin, otherwise you will rupture the cell. So that's why there is an MCQ that for recording of the RMP, which type of electrode is used. So look at the setup of resting membrane measurement, right? So resting membrane voltage measurement, according to Guyton, this diagram is given. So you can see here that this is the axons, or you can imagine that this is a cell, okay? And you want to measure the resting membrane voltage of this cell. So what you are doing, you are introducing one electrode inside this cell, okay? So this is the electrode which is placed just beneath the cell membrane, that is the interior of the cell membrane. And if you look at this electrode is filled with a solution. Could you understand what solution here? This is nothing but KCl solution. So please remember, this electrode are known as the microelectrode. Obviously, microelectrode means the electrode is very, very thin with a tip diameter of 0.5 micrometer. This was the MCQ. That for microelectrode, what should be the diameter of the tip? Less than 0.5 micrometer. And this electrode is made up of glass material, okay? So metals cannot be used for this kind of electrode. The glass is used. So you can imagine like this, that this is a glass electrode, and inside this glass electrode a solution is given, and that solution is KCl solution, and inside this solution one recording wire is kept, and this recording wire is connected with a very sensitive voltmeter, and other end of the voltmeter is connected with another electrode which is placed outside the cell membrane, as I told earlier. So with this kind of setup, you require microelectrode and you require very sensitive voltmeter, and with this you can record the resting membrane potential. But if you want to record the graphical image of resting membrane potential, or when the resting membrane voltage is changing, you want to plot a graph on a recording screen, then you require this cathode ray oscilloscope. So basically this cathode ray oscilloscope is an instrument which is just like a computer. Just imagine it's like a computer, it is a recording screen. If I want to plot a graphical representation of the resting membrane voltage, or when the resting membrane voltage is changing, if I want to plot, then this cathode ray oscilloscope will be used. This is nothing but like a computerized like screen, right? So this way you can measure the resting membrane voltage. Now the bigger question is that how the resting membrane is generated, right? So we are going to next discussion, that is origin of the resting membrane potential. Look at the first sentence, what is written here. Membrane potential, okay, resting membrane potential is caused by concentration difference of ions across a selective permeable membrane. Very important word. So concentration difference of ions should be present on E shape and I shape, means both sides of the membrane, as well as the membrane should be selectively permeable. Means if the membrane is equally permeable for all ions, then RMP is not going to be generated. Similarly, if there is no concentration difference between inside and outside of the cell, electrolyte difference I am talking about, then also resting membrane potential is not going to be generated. So, two basic condition is that there is uneven or unequal distribution of ion between E shape and I shape. And second thing, membrane should be differential permeable or selective permeable for different ion, right? So, if I want to understand the first thing, that uneven distribution of ion between E shape and I shape. So question will arise that why there is uneven distribution of ion between E shape and I shape. So first question, why the ion are unevenly distributed between E shape and I shape? And second question, that even if it is unevenly distributed, why they are not becoming equal? Means who is maintaining this unequal distribution of ion? So two questions, big questions are arising here. With this context, we are going to understand one effect which is known as Donan effect. Means this Donan effect has some role in uneven distribution of ion, or rather maintenance of the uneven distribution of ion. First thing, right? And second question that we are dealing here, that differential permeability of different ion in resting condition of the cell. So if I understand that this is my cell membrane, under resting condition, this membrane is selective permeable for different ion even in resting condition. If you recall my general physiology lecture, I told you the ions are generally impermeable through cell membrane. You require certain channels. So if I am saying that cell membrane is selective permeable for certain ion even in resting condition of the cell, that means certain channels are there which are open even during resting condition of the cell, and those kind of channels which remain open even during resting condition of the cell is known as leak channel. Please note down this name, leak channel, because these are the channel which are open even during the resting condition of the cell. Okay, they are always open, and that's why the ions are leaking through this, the ions are diffusing through these channels, and that's why they are known as a leak channel, and leak channels are responsible for generation of the resting membrane potential. Now whenever these leak channels are open, the ions will diffuse through them, the simple diffusion will continue to occur, and the main ion which will diffuse through these channels and which will be responsible for RMP generation is nothing but your potassium ion. So that's why the second point is written here, that contribution of the potassium diffusion is also responsible for RMP generation. And the third role is contribution of sodium potassium ATPase pump. We have seen the sodium potassium ATPase pump. It throws 3 molecules of sodium outside the cell and take back 2 molecules of potassium inside the cell. So this is an electrogenic pump, means if this pump is working, more positive charge is going out of the cell and less number of positive charges coming back. So what will happen? Automatically the membrane voltage will be a more negative side. So basically this sodium potassium ATPase pump, they keep the RMP in a more negative condition. Okay. Without the sodium potassium ATPase pump also RMP will be generated, because this point number 1 and point number 2 are more important. Okay, but with sodium potassium ATPase pump, RMP will be more negative than between these two condition. Okay, so suppose the RMP of a cell is minus 65 millivolt without sodium potassium ATPase pump. If the sodium potassium ATPase pump is added to this cell, then RMP will be more negative than minus 65. Right, that is the meaning of sodium potassium ATPase pump, and it is generally said that sodium potassium ATPase pump contribute only 5 to 10% of the RMP generation. The rest of the part are done by these 2 points, that is this effect of the uneven distribution, selective permeability and potassium diffusion potential. Now first we will be discussing this, the Donan effect. So what I told that Donan effect is responsible for maintaining the uneven distribution of the ion between ECF and ICF. Okay, so first question was why there is uneven distribution of ion between ECF and ICF. Look at this cell. So this is a typical mammalian cell and the composition of this typical mammalian cell is given here. Okay, you can find out here, this is the extracellular fluid and this is the intracellular fluid. This is taken from Guyton. As you can find out here, the sodium is high in the ECF and low in the ICF. Similarly, potassium is very high in the ICF and it is low in the ECF. Chloride is also very high in the ECF. Calcium is also very high in the ECF. So now my question is why the ECF composition is significantly different from ICF composition. Books are saying that this ECF composition is similar to the composition of the sea water from where life originated for the first time. What I am talking about? I am talking this thing that ECF concentration are thought to represent the concentration of this ion in seawater at the time the ancient ancestor left the sea. So life originated in the sea and our ancestor also originated from the seawater only. So this composition of the seawater is representing the extracellular fluid composition, but exactly same answer is no. During the process of this evolution, ECF composition, although the proportion of the seawater composition is still maintained, but during evolution, the ECF composition is gradually changing and today they are only 1/3 concentration in the seawater, right? So the ECF concentration of different ion, they represent the seawater composition. So now I can understand that if question is why there is difference between ECF and ICF composition, then my answer is that this difference is present from the origin point of the cell. Getting my point? So ECF and ICF composition, they are different from the origin point of the cell. Now more important question is that who is maintaining this difference? Why this difference is not becoming equal over time, right? So to answer that question, we all know that there are various pumps which constantly pumping certain ions and taking back certain ion inside the cell. There are various carrier protein which are also doing the similar kind of job. So if my question is how this ECF and ICF composition difference is maintained, so your answer will be that there are various pumps there are various carrier proteins are also there which are constantly working to maintain this composition. And the second, that how this composition is maintained, second is the effect of Donan effect, right? So second, how this composition is maintained, that is by Donan effect. So Donan effect, first thing first, you remember Donan effect is due to large impermeable molecule which is present mainly on one side of the cell. What I told, this is due to large impermeable molecule. The molecule should be large, it should be impermeable through the cell membrane, and then only the Donan effect will arise, right? So if you look at the concentration of protein in the ECF, it is very less, in the ICF it is very high. So I can imagine that intracellular fluid contain huge amount of protein in comparison to ECF or extracellular fluid. So how this protein is giving Donan effect, or what is this Donan effect? To understand this, look at this diagram. Okay, so on the first diagram, I am giving a semi-permeable membrane here. So this is a semi-permeable membrane. Dividing this box into two compartments. This is compartment A, this is compartment B. Now suppose I am giving sodium ion into this two compartment. Okay, so this two compartment contains solution, and within this solution I am giving sodium ion, assuming that this membrane is permeable to sodium as well as permeable to chloride. I am giving sodium, right? So how many sodium? Suppose I am giving 9 molecule of sodium positive charge ion on side B and 9 molecule of sodium on side A. So because they are equal in concentration, no question of diffusion will arise here. Now suppose I am giving 9 molecule of chloride on one side, that is side number B. Because the chloride is also permeable through this membrane, okay, so what will happen? The chloride will try to move on the other side, and after certain point of time there will be an equilibrium. I can understand like this. Equilibrium means 4 molecule of chloride will be here and 4 molecule of chloride will be here, and extra 1 molecule of chloride, it will move from here to here, and again it will move from here to here, right? That way I can understand that chloride is trying to distribute it equally on both sides of the membrane. Now, if I introduce one protein molecule on one side of this compartment, okay, now I am introducing one large impermeable molecule, that is the protein molecule, which is not permeable through this membrane, and I am giving this protein molecule on one side of the membrane. How many? 9 molecule of protein molecule, and they are negatively charged. Now this distribution of sodium, this distribution of chloride, everything is going to change. Why it is going to change? Because this protein, although it is not permeable through the membrane, but it contains negative charge. So this negative charge will attract more positively charged ion on this compartment, and this negative charge of protein will causes repulsion of more negatively charged ion on other compartment. Getting my point? So it is attracting more positive charge, that is sodium, and it is causing repulsion of more negative charge, that is chloride. So this will continue for certain time, and after certain point of time there will be an equilibrium condition. So this second diagram is after the equilibrium is developed. So after certain point of time, when the equilibrium has already developed, now if I look at the compartment A and compartment B, I can easily understand that the sodium ion will be lesser in this compartment, okay, that is suppose 6 molecule, and sodium ion will be higher in the compartment A, suppose that is 12 molecules, 3 molecule has been shifted to the compartment A, and chloride molecule, okay, that is negatively charged molecule, it will be chloride molecule is 6 here and chloride molecule is 3 here, right? So getting my point. So generally the chloride molecule should be equally distributed 4-4, but because the protein is giving the repulsion force on chloride, so more chloride has been shifted to other side, right? Okay, and more sodium has been shifted to side number A. Getting my point? And protein is present here, and how many protein molecules are present? The 9 molecule of protein are present, right? That is negatively charged, right? So this is the equilibrium condition. Now, first time this condition was described by Donan, okay, and that's why this is known as Donan effect. What Donan described? He described that due to presence of a large impermeable molecule, the distribution of permeable molecule changes through a semi-permeable membrane. Again I am repeating. Donan effect is saying that due to presence of a large impermeable molecule like protein, the permeable molecule distributed differentially on both sides of the membrane. So this permeable molecule in the form of sodium and in the form of chloride, they are differentially distributed. They are unevenly distributed in both sides of the membrane. That's why you are discussing that why the ECF and ICF uneven distribution is maintained. So this is a similar kind of effect which was first time described by Donan. So Donan is saying that due to presence of, so basically if I write a little bit, Donan effect is due to presence of a an impermeable molecule, impermeable molecule, the permeable molecule distributed, permeable molecule or ions distributed differentially on both sides of the membrane, differentially on both side of the membrane, okay, both side of membrane. So this is the Donan effect. Now when the Donan first time described this effect, later on Gibbs again look at this equilibrium and he told that we have to give some mathematical equation to this effect, otherwise people are not going to believe us. Okay, if you just say that due to presence of an impermeable ion, permeable ion distributed differentially, then no one will care. So you have to give one mathematical equation, and that's why the second one, that is the Gibbs-Donan equation. So Gibbs and Donan, they give some mathematical equation to this equilibrium condition. And what is that mathematical equation? So look at, in equilibrium condition, the number which I have already written here, these numbers are not random, they are maintaining certain equation. Okay, so what is that? Look at the total amount of charges, positive charges and negative charges on compartment A. Look at the total amount of charges in compartment A, positive charges and negative charges. What you are finding out? You are finding out the total positive charge on compartment A, that is 12, that is sodium, is equal to the total number of negative charges on compartment A, right? That means I can understand that in equilibrium condition, this compartment A is an electroneutral compartment. Total positive is equal to the total negative, electroneutral compartment. So this is the first equation of Gibbs-Donan equation, right? And obviously the total positive charges of compartment B is also equal to the total negative charges on compartment B, right? That means I can also understand that this compartment B is also an electroneutral compartment. That is the first equation. Then second, you look at the permeable ions only. Don't look at the protein, look at the permeable ion and look at their number. So sodium multiplied by chloride ion, okay, multiplied by chloride ion on compartment A is equal to the sodium multiplied by chloride, they are the permeable ion, on compartment B. So if you multiply this, sodium 12 multiplied by 3, 36, 6 multiplied by 6, that is 36, that is also equal. So the second equation, according to the Gibbs-Donan, they are saying that the product of the permeable ion, concentration of the product of the permeable ion on compartment A is equal to the product of the concentration of permeable ion on compartment B. So this is only for permeable ion product, right, not the impermeable. So now I can understand that due to this equilibrium, both the sides are electroneutral, right? Total amount of positive and negative is equal. But if I count the total number of ions on one side, total number of ions, okay, so inside A, total numbers of ions are very, very high, 12 plus 3 plus 9. But total number of ions on side B is very, very less. And we have already discussed that osmotic tension or osmotic pressure depends on the numbers of ions, numbers of active molecules, right? So obviously, due to huge number of ions on side A, the osmotic tension of side A will be very, very greater than side B. So these three are the equation proposed by Gibbs and Donan, and that's why this is known as Gibbs-Donan equation. And I told you first time the effect was described by Donan, and that is known as Donan effect, right? So now with the help of this Donan effect, we can conclude that inside of the cell and outside of the cell both are electroneutral. What I am talking about? Okay, try to understand. So now I am drawing one cell here, okay? So this is one cell. In this cell, I am saying that if I look at the ICF, the total number of positive charge, will be equal to the total number of negative charge, right? That is the meaning of electroneutral. Getting my point? We are just understanding the Donan effect with respect to cell. So if I look at the intracellular fluid, the large portion of the intracellular fluid, they are electroneutral, right? Similarly, if I look at the extracellular fluid, okay, again it will contain equal number of positive charge, equal number of negative charge, means again the ECF also they are electroneutral, okay, right? But still we are saying that if we measure the charges between inside of the cell membrane with respect to outside of the cell membrane, there will be difference in charges, there will be difference of voltage, and that is known as RMP. So these are basically looking like contradictory statement. You are saying that interior of the cell is electroneutral and exterior of the cell is also electroneutral, but still you are saying that inner leaflet of the membrane and outer leaflet, there is a difference of charges between these two leaflet of the membrane, and that is nothing but resting membrane voltage. So what is happening? How this charges difference is generated, right? So now we have to think about the leak channel. So second point, I told that in resting condition, certain channels are open on cell membrane. Those channels are known as leak channel. I told you already. So now again I am drawing a cell. Okay. So I am drawing another cell. Okay. And this cell under resting condition, they contain certain leak channel. Right. Which leak channel I am talking about? In mammalian cell, most of the cases, leak potassium channel is also present, leak chloride channel is also present, leaky sodium channel is also present. Okay. So what I am saying, for most of the mammalian cell, all these three types of leak channels are present in resting condition. Leak channel means they are always open, even they are open in the resting condition also. But our understanding will be very easy if we assume that our mammalian cell contain only one type of leak channel, that is potassium. Okay, we'll be understanding that if all three are present, what will happen? But first, look at the simplest form. So, we are assuming that this cell contain only one leak channel, and that leak channel is leak potassium channel. We are assuming this simplest form of cell. Is there any example of this kind of cell where only potassium leak channels are present, other leak channels are also not present? Answer is yes. This is nothing but example of a glial cell. Okay, glial cell, right? They contain only one type of resting channel, and that is leak potassium channel. So because it's a mammalian cell, the potassium concentration will be very, very high. We all know. So potassium concentration inside the cell is very, very high in comparison to outside potassium concentration. But we have just discussed that whenever one molecule of positive charge is present inside the cell, it is not alone. Positive charge is always in couple with a negative charge. Understand the concept. What I am saying, just now we have discussed the interior of the cell as well as the exterior of the cell, they are electroneutral. Here I am taking potassium as my positive charge. So obviously there will be a corresponding negative charge along with potassium. This negative charge may be anything. We are not interested in that because that negative charge is not permeable through cell membrane. Why we are considering potassium here? Because the cell membrane is permeable to potassium. That's why we are writing positive charge as potassium and corresponding negative charge. Whatever may be the negative charge, I am not interested. Right. Similarly, the outside potassium will also accompany by a corresponding negative charge. Right. They are couple. Right. Positive, negative, they are making a couple. Right. So whenever the potassium concentration is very, very high inside the cell, the potassium will try to move through this leak channel. Right. Obviously. So why the potassium is trying to move? Because of concentration gradient, which is known as chemical gradient. So I am writing here, because of chemical gradient, or because of concentration difference between inside and outside the cell membrane, potassium will try to move from inside to outside. Very simple, through this leak channel. So now the potassium is trying to move. So potassium is going towards the channel, but it is not moving alone, couple. So it is moving along with a corresponding negative charge. But whenever it is reaching at the gate of this channel, now this gate is very selective. It will allow only the potassium. It will not allow the corresponding negative charge to pass through. So what is going to happen? Whenever the potassium is moving towards this channel along with a corresponding negative charge, the potassium will easily pass through because the channel is dedicated for potassium. Okay, but it will not allow the corresponding negative charge to pass through this channel, and the negative charge will be deposited here. Getting my point? Like for example, what happens in immigration, right? If your documents are not proper, so you will be stopped there. And the same thing is happening for this negative charge. Negative charge is not allowed to pass through, but positive charge potassium is allowed to pass through because the channel is dedicated for it. So now I can understand more and more potassium is trying to pass through this channel. Okay, more and more negative charge will be deposited in inner leaflet of the membrane. Getting my point? So potassium is moving due to concentration gradient. More and more potassium is moving out. Corresponding negative charge is depositing on inner leaflet of the membrane. So I can understand. So now the cell membrane is getting extra positive charge on outside the cell membrane in the form of potassium, and the cell membrane is getting extra negative charge inside the membrane due to this potassium movement only. So potassium diffusion is happening, and that's why the inner and outer leaflet of the membrane is getting different charge. Now question is, how long this diffusion of potassium will continue? Answer is there will be an equilibrium condition. So what do you mean by equilibrium? So suppose 5 molecules of potassium already moved out of the cell. Already the 5 molecule of potassium has gone out of the cell from inside to outside. Now whenever the 6th molecule of potassium is trying to move out, okay, this outside positive charge will causes repulsion of the 6th molecule of potassium. Getting my point? So this 5 and 6, these numbers are just arbitrary numbers. Suppose sufficient amount of potassium already moved out of the cell, and whenever the extra amount of potassium is trying to move out, that will be pushed inward by extracellular positivity. So whenever this 6th molecule of potassium is trying to moving out, the electrical gradient, now the electrical gradient or electrical force is trying to push the potassium inside the cell. Okay, so concentration gradient is pushing potassium out of the cell. Okay, after certain amount of potassium movement, what will happen? Some molecule of potassium will also come back, okay, inside the cell. So I can understand that this movement will continue for certain amount of time, and then there will be development of an equilibrium condition. So after certain point of time, okay, there will be development of an equilibrium condition. Equilibrium condition, okay. Equilibrium condition means what kind of equilibrium? This equilibrium has been developed due to electrochemical gradient. Electrochemical gradient or electrochemical forces, right? Chemical forces is pushing the potassium out, electrical forces is pushing the potassium in. What do you mean by this equilibrium? Equilibrium means at this equilibrium point, the net movement of potassium, the net movement of potassium through the leak channel is 0. Getting my point? So the potassium was moving through this leak channel. He is moving. After a certain point of time, equilibrium developed. During that equilibrium, whenever extra potassium is trying to move out, that potassium is coming back to the cell, and that is known as equilibrium point. That means at equilibrium point, the net movement of potassium through the leak channel is 0. But we have already discussed that due to movement of this potassium, certain amount of negative charge has been deposited in the inner leaflet of the membrane, and certain amount of positive charge has already been deposited on outer leaflet of the membrane. So even at this equilibrium condition, if I measure a voltage difference between inside and outside, inside voltage I am measuring with respect to outside, then what I am going to get? I am going to get this voltage difference, and that voltage difference which you are measuring at equilibrium condition of the cell, this is known as equilibrium potential of the membrane or isoelectric potential of the cell. Isoelectric potential of this cell. So equilibrium potential or isoelectric potential, what is that? In equilibrium, when the cell is in equilibrium, the inside of the cell membrane contains certain negative charge with respect to outside, and if I measure that voltage, this is nothing but known as equilibrium potential or isoelectric potential. So if I question that in this glial cell, can I measure this equilibrium potential? Why not? Very easy. For measurement of this equilibrium potential, just introduce one electrode inside the cell, we have discussed earlier, and you placed one microelectrode outside this cell. In between these two electrodes, if you connect one voltmeter, that will record the equilibrium potential. But suppose I don't have this microelectrode, I don't have this very sensitive voltmeter. Can I calculate this equilibrium potential by some mathematical equation rather than this kind of setup? Answer is yes. And this calculation of equilibrium potential or isoelectric potential is done by a equation, and that is known as Nernst equation. This is known as Nernst equation. So what is Nernst equation? It is nothing but giving mathematical calculation of equilibrium potential is done by an equation which is known as Nernst equation. So according to the Nernst equation, now we look at the equation, very important for Central Institute examination and obviously NEET also. According to Nernst equation, equilibrium potential of an ion is equal to EQ, is the equilibrium potential, is equal to R T Z F, log of concentration of the ion. Suppose I am considering ion X, I want to measure the equilibrium potential of ion X, concentration of the ion outside the cell upon concentration of the same ion inside the cell. If I know what is the concentration of the ion outside and inside the cell, and then you put this concentration in this equation, you are going to get the equilibrium potential of the ion, right? Now generally this equation is written like this, plus minus, but I am not putting plus minus. Why? You will understand. So now we look at, I am simplifying this thing. So this equation is given in natural logarithm. So this log is the natural logarithm. So if I want to convert this natural logarithm to log base 10, so I have to multiply this with 2.3. So 2.3 R T Z F, log base 10, concentration of the ion X outside the cell and concentration of the ion X inside the cell, right? Now this R, T and F, so this R, T upon F, this whole fraction is a constant, the gas constant. R is the gas constant, T is the absolute temperature, and F is the Faraday constant. We don't have to understand all these things. This is basically the core physics, but we have to remember that this is a constant, and the value of this constant is 26.7 millivolt at 37 degree centigrade temperature. So this constant RT upon F, what is the value of this constant? That is 26.7 millivolt at 37 degree centigrade, that is the core body temperature. Now if you change the temperature, then this constant will also change, the number of this constant will also change, and that's why this Nernst equation, different books has given different value, because most of the experiment is done on seawater, their temperature is different from our body temperature, but we are considering the human cell, there the core body temperature is 37 degree centigrade. So if we consider 37 degree centigrade temperature, then this RT upon F this has a value of 26.7. So if I multiply this 26.7 with this 2.3, this will be plus 61 millivolt upon your Z, then log base 10 concentration of the ion, this is same, out, and concentration of the ion X inside the cell. So this is the simplified version of this Nernst equation. So now the EQ is equal to plus 61 millivolt upon Z, then log base 10 concentration of the ion X outside and concentration of the ion X inside the cell. This is the Nernst equation, right? So what is this Z? This Z is basically the valency or the charges of the molecule that I have to write. So if it is sodium, I will write down plus 1 for Z. If it is calcium, I will write down plus 2 for calcium. Okay, if it is chloride, I will write down minus 1. So with this concept, suppose I am giving you a problem. Okay, not just problem, basically just to give you an idea how to apply this equation if mathematics is given in your exam, right? So suppose this cell contain potassium concentration inside, and that is 140 milliequivalent per liter, and potassium concentration outside is 14 milliequivalent per liter. Obviously this is not like a normal mammalian cell, because in normal mammalian cell outside potassium is not 14, but this is a model cell. Okay, model cell, and in this model cell potassium inside is 140, potassium outside is 14. Calculate the equilibrium potential of potassium in this cell. So equilibrium potential of potassium in this cell, we are going to apply this formula, that is plus 61 millivolt upon Z. Z is potassium plus 1 log base 10 concentration of the potassium outside the cell is 14, concentration of potassium inside the cell is 140, right? So now I can understand that this log 10, this is 1 upon 10, log 1 upon 10 with base 10. What is the value of that? We know this has a value of minus 1. Okay, log 1 upon 10 with base 10, that is minus 1. So now this whole fraction will be minus 1 and it will be minus 61 millivolt. So I can understand in this cell the equilibrium potential will be minus 61 millivolt. That means the inside of the cell will be negative and outside of the cell will be positive. If I measure this voltage difference between inside and outside, inside with respect to outside, that will be minus 61. The cell is permeable for only one ion, and that is the potassium ion. Similarly, if I give you another example, suppose this cell, okay, this is permeable to only chloride. This cell is permeable to only chloride molecule, and outside chloride concentration is 110 milliequivalent per liter. Inside chloride concentration is only 11 milliequivalent per liter. So I am giving this number just for my calculation easiness. Okay, otherwise I require a log table. I hope you understood that. Okay, so otherwise you require log table. So in this condition, what I'm going to calculate? I'm going to calculate the equilibrium potential of chloride. So again the same formula, plus 61 upon Z. So I'm going to write down minus 1 here. Okay, that is the charge of chloride. Then log base 10 concentration of chloride outside, that is 110, inside is 11. So this fraction is nothing but 10. So log 10 base 10. So log 10 base 10 is nothing but plus 1. So if I multiply plus 1 with this whole fraction, again it will be minus 61 millivolt. Getting my point? So even in this cell also, inside voltage will be negative, outside voltage will be positive, and how much that is? That is minus 61 millivolt in equilibrium. That is known as the equilibrium potential of chloride in this cell. So in both this example, we have taken a model cell, okay, but exact concentration of chloride inside the cell is not 11, okay, and similarly exact concentration of potassium is not 14 outside. So if we look at the mammalian cell, typical mammalian cell, what is the equilibrium potential of? Okay, I'll write down here. So if we look at the normal mammalian cell, okay, what is the equilibrium potential of different ion? Equilibrium potential of different ion in a normal mammalian cell. Remember this value, very important. Sodium equilibrium potential is plus 63 millivolt. Chloride equilibrium potential is minus 70 millivolt. Okay, potassium equilibrium potential is minus 90 millivolt. Calcium equilibrium potential is plus 132 millivolt. Means if you put the exact concentration of potassium inside the cell and outside the cell, you are going to get the equilibrium potential of minus 90 by Nernst equation. So all these values, it has been calculated with the help of Nernst equation, considering the concentration of a normal mammalian cell at 37 degrees centigrade temperature. Right? Okay. Some of the books are saying sodium maybe plus 63 to plus 65. That's okay. I told you already that depends on the constant. That constant is going to change along with temperature. Okay. Some of the books are saying it is from minus 65 to minus 70, and this potassium is minus 90 to minus 94 millivolt. That's okay. Okay. And calcium is plus 132 only. Right. So that's okay. But we are going to remember this red color number. This is very, very important. This is the equilibrium potential of different ion. Right. Now, I am putting another question in front of you. So, I have a glial cell. Okay. I have a glial cell, and we have already understood that glial cell contain only one type of leak channel, and that is leak potassium channel. Okay. Leak potassium channel. So, in resting condition, in equilibrium condition, what will be the potential difference between this inside and outside of this cell membrane? Obviously, you will be able to answer. What will be the equilibrium potential, or what will be the resting voltage difference between inside and outside this cell membrane? Answer is minus 90 millivolt. Where from this minus 90 is coming? Minus 90 is the equilibrium potential of potassium. Now, if I ask you, what is the resting membrane potential of this glial cell? So, what is resting membrane potential? Resting membrane potential is the potential difference across the cell membrane between inside with respect to outside in resting condition, and we know resting condition means that is nothing but a equilibrium condition of the cell, and we have already understood the equilibrium condition, the cell is maintaining a potential of minus 90. So, the RMP of this glial cell will be equal to the equilibrium potential of this potassium ion, and that is nothing but minus 90 millivolt. So, what is the bottom line? The bottom line is that if a cell contain only one type of leak channel, that is here the potassium leak channel, okay, only one type of leak channel, then the RMP of that cell will be equal to the equilibrium potential of the ion which is permeable to that cell membrane. Getting my point? So, I am writing this very, very important statement, very, very important statement. Remember, if membrane is permeable to, membrane is permeable to only one type of ions, only one type of ion, okay, then in this cell the RMP is equal to equilibrium potential of that ion. Getting my point? Very, very important. So, if I ask you a question like this, okay, model question, that one cell membrane is permeable to only chloride ion, what is the RMP of that cell? Your immediate answer will be RMP of that cell will be minus 70. If the cell membrane is permeable to only sodium ion, what will be the RMP of that cell? Plus 63 millivolt, because that will be in equilibrium, right? Similarly, if the cell membrane is permeable to only potassium, then what is the RMP of that cell? Minus 90 millivolt. Getting my point? Right. Okay. So now, question is our mammalian cell is permeable to only one type of leak channel, only one type of ion? Is this statement is true for all mammalian cell? Answer is no. We know that this statement is true for glial cell because that is permeable to only one type of ion. But this is not true for all mammalian cell, because earlier I told you almost all of our mammalian cell, they are permeable for three different types of ion. Okay, three different types of ion. What are those? So they are permeable to potassium, Okay, they are permeable to potassium, permeable to chloride, permeable to sodium only. So let's try to understand the scenario in case of typical mammalian cell. Right. So typical mammalian cell, it contain leak potassium channel also, leak chloride channel also. Okay, leak chloride channel also, and leak sodium channel also. Okay, so whenever one cell membrane contain all three types of leak channel, every channel will try to develop their equilibrium potential. Equilibrium means that is a very comfortable condition for ions, right? Getting my point. So potassium, he will try to develop a equilibrium condition so that it become comfortable for him. Chloride will also try to do the same, and sodium will also try to do the same. But if we look at the equilibrium potential of all of them, so this is minus 90, this is minus 70, and this is plus 63. Means in this cell, if I think of RMP, then RMP will move maybe towards this side or will move maybe towards this side. Means RMP is moving here and there. Where the RMP will stop? Okay. In case of single ion permeable cell, RMP will stop at the equilibrium potential. But here 3 ions. So whenever 3 ions are permeable through a cell membrane, all will contribute for the generation of the RMP. Potassium will say that the RMP will be equal to my equilibrium potential, that is minus 90. Sodium will say, no, I am also there, equilibrium potential. Okay, I will try to develop equilibrium potential, and RMP will be close to my potential, that is plus 63. And chloride will say, yes, I am also there, consider me. I will try to make the RMP at minus 70 millivolt. So all of them are fighting with one another, and RMP is moving in this side, moving here and there, deciding where to stop. Ultimately, the RMP will move close to that ion which is strongest among all these three. Strongest means, look at the number of these ion channels. Numbers of this ion channel. Which numbers? Okay, potassium, chloride or sodium, which numbers are maximum? If you look at the numbers or if you look at the permeability, then leak potassium channel numbers are very huge. That chloride channel number, that is very huge than leak sodium channel number. That means I can understand that in resting condition, permeability of the potassium ion is maximum in comparison to chloride, which is maximum than sodium ion also. And if I look at the permeability coefficient, this is known as permeability coefficient of these three ions. If it is 1 for potassium, okay, for chloride it is 0.45 and for sodium it is 0.04. That means if I want to simplify this thing, in a resting cell, if 100 leak potassium channels are open, only 45 leak chloride channel will remain open and only 4 sodium channel will remain open. That is the meaning of the permeability coefficient. So now I can understand, although these three ion channels, they are fighting with one another for development or generation of the RMP, the potassium is the strongest because of its maximum permeability, and that's why this RMP will move close to the equilibrium potential of potassium. That's why we say that RMP of almost all the vertebrate cell is close to equilibrium potential of potassium. Why that is true? Because potassium is the maximum permeable ion. Potassium is the maximum permeable ion in resting stage of the cell. But if I ask you, RMP is generated by which ion? Only potassium? No. RMP is generated by all these three ions. It is contributed by potassium ion. It is also contributed by chloride ion. It is also contributed by sodium ion. But the contribution of potassium is maximum than chloride than sodium. So now I can understand that if the question is RMP is close to equilibrium potential of which ion, then they are asking you a concept that in resting condition which ion is maximum permeable through cell membrane. And if it is maximum permeable, RMP will move close to that ion. And that's why, okay, you have to remember that RMP is close to equilibrium potential of potassium, in almost all the vertebrate cell. It may be neuron, it may be myocardium, it may be muscle cell, any kind of cell. If the question is RMP is close to, that means they are asking which ion is maximally permeable in resting stage. But if the question is equal to, the answer is different. That I am discussing a little later. But for the time being, you require this basic concept to remember that if the cell membrane is permeable to only one type of ions, then RMP is equal to equilibrium potential of that ion. And how to calculate the equilibrium potential? By Nernst equation, right? But if the membrane is permeable to three different types of ion, then all will contribute for generation of the RMP, but the maximum contribution will be given by ions which is maximally permeable in resting condition. That's all. So now my last question, that can you calculate RMP by Nernst equation? Nernst equation we have discussed earlier. Here, this is a Nernst equation. If you look at this Nernst equation, this is only for a single ion. Look at, we are placing only one ion concentration in the log value. Only one ion. So remember, Nernst equation is applied for only one ion. But just now we have understood that RMP is contributed by three different types of ion. So can I calculate RMP by Nernst equation? Answer is no. If the cell membrane is permeable to only one type of ion, then RMP will be calculated by Nernst equation also, because in that cases RMP is equal to equilibrium potential. But if the cell membrane is permeable to more than one ions, typically 3 ions, then RMP cannot be calculated by Nernst equation. So I have to take help of another equation, and that equation is written here. Okay, I have directly copy pasted from Guyton because this is a long equation. You can find out Vm, that is a membrane voltage, is RT upon F. Same thing. This is a natural logarithm. Okay, natural logarithm of P is the permeability, and this is the concentration. So permeability as well as concentration, both are considered in this equation. Similarly here, this P is the permeability of sodium, and here sodium concentration. And again, this is chloride permeability and chloride concentration. This I stands for inside concentration of chloride, O stands for outside, O stands for outside concentration. So this is a complex equation. If you put all the value of this permeability as well as the concentration of these 3 ions, then you are going to get the RMP of that cell. So this equation is known as Goldman Hodgkin, okay, Goldman-Hodgkin-Gaz equation. That's scientist. Okay, so Goldman, Hodgkin and Gaz, they developed this equation. That's why this equation is known as Goldman-Hodgkin-Gaz equation. It is also known as Goldman constant field equation. This is also known as Goldman constant field equation. Okay, Goldman constant field equation. Okay, so this way you can calculate the RMP of different cell with the help of this equation. So if you want to remember the RMP of the different cell, this is here. This table I have taken from Guyton. So as you can find out here, the neuron has an RMP of minus 60 to minus 70, but we are going to remember minus 70 millivolt. So resting membrane potential of neuron is minus 70 millivolt. Minus 70 millivolt is the equilibrium potential of which ion? Chloride ion. Yes, right. Okay, so skeletal muscle has an RMP of minus 90 millivolt. I am going to remember this. Okay, so minus 90 millivolt, although the range is given. Similarly, smooth muscle, you have to remember this range because smooth muscle RMP is not a fixed voltage, so it is a range. Cardiac muscle, okay, again the RMP is minus 90 millivolts, similar to skeletal muscle. Okay, hair cells, okay, there is difference in hair cell RMP. So normally you remember minus 15 to minus 40 millivolt. Okay, but later on I will tell you that hair cell RMP can be different if you measure with respect to endolimb or perilimb. Okay, that will be discussed in special sense chapter. Then astrocyte, okay, just now we were discussing the glial cell. There has an RMP of minus 90 millivolt because that is the equilibrium potential of potassium ion. Then erythrocyte on an average has an RMP of minus 10 millivolt, right? And the photoreceptor, that is the rods and cone, their RMP changes during the dark condition and light condition. You must have to remember this, that in dark condition, this is minus 40 millivolt, and in light condition the RMP is more negative, that is minus 70 millivolt. Very important for MCQ. We will be discussing this thing in special sense topic also, but for the time being remember this value. So now we have understood how the RMP is generated and what is the RMP of different cell. So now you recall these three bottom line that we have already discussed. So resting cell membrane is most permeable to potassium ion, but permeability of potassium is greater than chloride, greater than sodium. We have discussed this, but it has to be input in your brain, okay, and never forget this. Now RMP of almost all vertebrate cell, maybe neuron, maybe skeletal muscle, maybe anything, any cell, RMP of all vertebrate cell is close to equilibrium potential of potassium. But whenever the question is equal to, so RMP of neuron and the question is equal to, so I am asking myself what is the RMP of neuron, that is minus 70 millivolt, just now we have discussed, and it is equal to, exactly equal to same number, okay, with the chloride equilibrium potential, because that is also equal to minus 70. But whenever I am giving a different question, that RMP of myocardium, what is the RMP of myocardium? RMP of myocardium is minus 90 millivolt. So if I ask you RMP of myocardium is equal to, then I have to search on ion which has an equilibrium potential of minus 90, and that is nothing but potassium, which has also an equilibrium potential of minus 90. So look at, if the question is equal to, then it is same to same, number same to same. But whenever I am asking you close to, maybe neuron, okay, maybe myocardium, in all the cases close to means they are asking you the concept that which ion is maximally permeable in resting condition, RMP will be close to that ion equilibrium potential, and the answer here always potassium. Getting my point? Please note down this very important thing. So this is all about generation of RMP. So we'll do certain MCQ so that your concept will be more stronger, okay. So first MCQ, equilibrium potential of an ion is calculated using, okay, this is a very simplest equation nowadays, okay. Equilibrium potential is calculated by Nernst equation, right? Equilibrium potential is calculated by Nernst equation. Gibbs-Donan equation we have discussed already, that due to presence of a large impermeable ion on one side of the membrane, and Goldman-Hodgkin-Cash, that is for calculation of the RMP, okay. So, and Donan equation, that is the same thing like that of the Gibbs-Donan equilibrium, okay. Then second, resting membrane potential is close to, what they are asking, close to, so close to any cell, I'll put answer as potassium, because they are asking the concept, okay, that maximum permeability. Then resting membrane potential of nerve and equal to, now they are asking equal to, same to same, so minus 70, okay, and chloride equilibrium potential of also minus 70, so here the answer is chloride. And the next question, in a hypothetical cell model, the ratio, okay, the ratio of extracellular and intracellular calcium concentration is 10,000:1. Calculate the equilibrium potential of calcium in this cell. So what they are asking you, they are asking that this is a model cell. In this model cell, they are giving you the concentration of calcium between outside and inside is 10,000:1. So I am going to calculate the equilibrium potential of calcium in this ion. So the same formula I am going to use, that is the Nernst equation. So according to Nernst equation, plus 61 upon Z, I hope you recall Z. So Z is plus 2 because it is calcium, right? So this is Z. Then log base 10, outside concentration is 10,000. Inside concentration is 1. So this is 10 to the power 4. So we all know that log 10 to the power 4 with base 10 is equal to 4 only. So if this is the thing, then 61 multiplied by 4 upon 2. So basically this is 122, right? So that's why it will be positive, it will be positive, it will be positive. So answer here will be plus 122. If this is the thing, then none is the answer, but answer will be plus 122 millivolt. Getting my point? So even if you confuse between negative or positive, that whether the equilibrium potential will be negative and positive, just calculate the number with the help of this Nernst equation. Just listen. Why I'm saying, because you know that this is a log 1. This is a log 1. So if you change outside, inside, inside, outside, then the log value will change. It will be negative and positive. That way, if you forget that the numerator and denominator, what was that? Outside concentration or inside concentration? What was that in that equation? You forgot. Okay. Then you just calculate the number with the help of Nernst equation. And whether it will be positive or whether it will be negative, try to apply your concept. What is that concept? That in this cell, calcium is high in outside the cell membrane. So what will be the natural diffusion of calcium? From outside to inside? That is the natural way of diffusion of calcium. So if the calcium is diffusing from outside to inside due to concentration gradient, so obviously inside will be more and more calcium, inside will be positive. So equilibrium potential will be positive in case of calcium. Getting my point? Similarly, if I ask you, the cell is permeable to potassium ion. So this is the potassium leak channel. So what is the natural diffusion of potassium from inside to outside? So I can understand like this, that the cell is losing potassium. The cell is losing positive charge. Losing positive charge means inside of the cell will be negative, and inside voltage we always take into consideration. So equilibrium potential of potassium will be negative. Similarly, if I ask you that this is chloride, okay, chloride. So we all know that chloride ion is very high in outside the cell membrane. So the normal diffusion is from outside to inside. So negative ion is moving from outside to inside. Inside of the cell will get more negative charges. So again, the equilibrium potential of chloride will be negative. So that way, if you look at this previous discussion here, okay, if you look at this previous discussion here, that equilibrium potential of different ion where I have written, okay. So that's why you are finding out that equilibrium potential of sodium is positive, because sodium moves from out to in, positive charge is moving. Equilibrium potential of calcium is positive because calcium moves from out to in, and that is a positive ion. Equilibrium potential of chloride is negative because chloride moves from out to in and negative ion is moving inside the cell. And equilibrium potential of potassium is also negative because potassium is moving from in to out. The cell is losing positive charge, so inside of the cell will be negative. That's why the equilibrium potential sign, whether it will be positive or negative, you can remember like this, and this number, this will be calculated based on the Nernst equation. So this is all